And we will start with the first presentation, that is a presentation organized by the Cluster Tecnológico de Córdoba. The topic is Innovation, the Career on Quantum Computer, in charge by Mark Jackson, who is a quantum evangelist in quantum technology, and he got a university in Duke with a doctorate in physics in Columbia. Then he spent 10 years investigating the superquarks and cosmology, and he has been a co-author of many articles. He's an adjunct professor in Singularity University and directors of Astronomers Without Frontiers. And the moderator of the Q&A session will be Omar Osenda, doctor in physics and researcher of the National University of Córdoba, and he will moderate the Q&A session. Before that, Omar will welcome Mark, who is already there.
Placer estar aquí en esta reunión en nombre de los organizadores de la organización. Quisiera agradecerte, Mark, porque esta presentación está siendo esperada con mucha ansiedad. Y pienso que tenemos un grado bastante alto de ansiedad porque todos escuchan sobre la computación cuántica, como la carrera para obtener la primera computadora y los otros avances. Entonces, que en cuanto a los detalles, vas a tener que hablar por alrededor de 40 minutos y después va a haber 15 minutos más o menos para preguntas y respuestas del público, y yo voy a tratar de redireccionar todas esas preguntas para vos. Todos pueden mandar sus preguntas, no hay ninguna pregunta que sea tonta, es un tema muy amplio. Mark, tenés la palabra.
Hola a todos, un placer hablar contigo hoy. Hablo un poco de español, pero será más fácil en inglés. Yes, so I'll have to do this in English, I'm sorry. So let me share my screen here. And I think you should be able to see that there. So I have the pleasure of telling you about quantum computing today. I am the quantum evangelist at Cambridge Quantum Computing. So I'd first like to just say a few words about the company that I work for. We focus exclusively on quantum computing and related technologies. We're about 7 years old, which makes us one of the oldest quantum computing companies. We have about 150 people, but we are in the process of merging with Honeywell's quantum group, and we will soon be the largest quantum computing company in the world. We have several different focus areas, including quantum chemistry, machine learning, compilers, and cybersecurity. And we're focused on near-term applications of quantum computing. So it's not just things in 20 years. We'd like to accomplish things in the shorter term, in the next few years. So I'd like to begin by introducing what is usually thought of to be the very first computer by Charles Babbage about 200 years ago. And even though this looks comically antiquated by today's standards, it actually has all the ingredients that we would identify in a modern computer. It has input devices and it has output devices. And in particular, the way that it stores and processes information is identical because it actually just uses tiny little switches, which are either on or off. And if you compare that to today's computers, like the laptop that I'm using to give this presentation on, we've obviously come a long way in terms of computational power and how easy it is to use, but this core idea is identical. And so what I'll be telling you about today is really the first breakthrough in 200 years in the way that we think about and calculate information. So by way of a very brief introduction to quantum computing, I just wanted to point out the difference. Normal computers work with bits, which are ones and zeros, on or off switches. Quantum computers work with quantum bits, or qubits, we call them. And a qubit can be a 0 and a 1 at the same time. And it's a bit like with coins. A normal computer works with a coin which is on a table. So it's heads or tails. It's one or the other. But a quantum computer works with a coin which is flipping in space. So it can be anywhere in between the 0 and 1. And when you combine that with another quantum physics concept called entanglement, you can unlock a huge number of states, we say. And I'll explain why this is so important in a moment. So on the upper left-hand corner here, this is my favorite molecule, caffeine, and it's not terribly large. It only has 24 atoms. But if you were to put this on a computer to simulate, you would need a computer about 1 to 10% of the size of the Earth. So that's theoretically possible, but it's not very practical. If you made the molecule just a little bit bigger, say 41 atoms, you could do it, but you would need a computer the size of the entire universe. So that's kind of the end of the theoretical limit. Even if you used the whole universe to make a computer, you wouldn't really be able to simulate it. And so this is why we thought of building quantum computers, because there are a lot of problems in science that we want to solve, but we never could solve them using normal computers. And if you look at the right-hand side of the screen, you see that with very modest requirements in quantum computing, with only a few hundred qubits, we can simulate this. And so that's why we're so excited. We could solve problems that we never could have hoped to have solved before. Just to give you some idea of how many qubits we're dealing with, Google and IBM predict that they will have 1,000 qubits in another 2 years, and they will have 1 million qubits within 10 years. So this is very much within the realm of possibility of things that we could do in the next few years. Quantum computing will not just be one new thing. It will actually change every area of science and technology. So this is a kind of an overall schematic of all the different areas that we're learning about. And so we have quantum simulations and communication and algorithms and machine learning and chemistry. I could spend a long, long time talking about each of these. Unfortunately, I only have a few minutes to tell you what's happening. And so I'd like to focus on just the most important aspects. If there's one thing that I wanted to communicate to you today, it's that quantum computers do exist. This is not science fiction, fantasy, buzzword type things that we're talking about. They really do exist. They've existed for several years now. People program them. We're doing amazing things with them. On the left-hand side, this is a picture of one of IBM's machines. And you notice that it kind of looks like a chandelier that you would lower down. So the reason you don't usually get to see this, the center of the quantum computer, is because we usually put it in a giant refrigerator, which is kept near absolute zero. And this is because this type of technology, called superconducting, needs the materials to be at almost absolute zero before it can get these special quantum properties that we can take advantage of. The quantum computer on the right is one of Honeywell's machines, and it uses a different technology called ion trap. So it uses lasers to trap charged particles called ions, and then it can manipulate those as we wish. And each of these has its own advantages and disadvantages. It's not clear which type of technology will be the winner. There will probably be several winners. And so intense work and resources are being put into this right now. So these are some of the other groups. We know of over 100 quantum computers in the Western Hemisphere alone. So I've mentioned the superconducting approach, which is being used by IBM and Google and Rigetti. There is the ion trap, which I showed you is being used by Honeywell and IonQ. And there's also photonic and a few other approaches. And again, each of these has their own advantages and disadvantages. It's sort of like a marathon after 1 mile. Different groups are using different strategies, and it's not at all clear who's going to win. There was a big development about 2 years ago called quantum supremacy. And this was a result by Google and collaborators in which they found an example of something that a quantum computer could do that a normal computer couldn't do. And it wasn't a particularly useful example, but it was one thing that a quantum computer could do in a few minutes that would have taken a long, long time, like hundreds of thousands of years, on a supercomputer. And this has been evaluated and confirmed by the outside community. And so we still have a lot of work to do, of course, but it was a major milestone. And some people before this even had doubts about whether quantum computers could do anything that a normal computer couldn't do. It's not just the number of qubits that's important. It's also the quality of the qubits and how they're arranged. And so that's why there's been this metric introduced called the quantum volume. And it's a complicated formula to how to compute the quantum volume, but it takes into account all of these things. And so there's a single metric that we can use to evaluate the power of a quantum computer, and we can use it to compare different quantum computers. And so this is a chart showing the progress made by different quantum groups. And so I think many of you are probably familiar with Moore's law, in which the power of normal computers has doubled every 18 months or so. The blue line shows the progress just made by IBM, and they've actually been able to more than double the quantum volume every 12 months or so. And so that's a little bit faster than Moore's law. The orange line shows the progress made by Honeywell, and they're on a much faster trajectory. They've been able to increase the quantum volume by about a factor of 10 every year, and that they think that they can sustain this development. And so in a few years, we should see some really amazing results from quantum computers. This is what a quantum program looks like. And you see that it's unlike anything that you would put into a normal computer. So the horizontal lines represent qubits, and you read this from left to right, sort of like a musical score. So on the left-hand side, there's the initialization of each of the qubits. And so we usually initialize them into the 0 state, and then we apply different operations. So you see some of these operations act on just one qubit, like those blue H operations. And some of the operations combine 2 qubits, and there's an interaction between them. And so you have all these different operations, and then at the end, you measure the qubits. And only when you measure them do you force them to choose 0 or 1. So up until then, they're in this superposition or entanglement state, and you don't ever get to peek at what they're doing. But on the measurement, you're forcing them to choose, are they 0 or are they 1? And it's probabilistic on which one they'll choose. And then, of course, once the measurement is done and it's a 0 or a 1, then it's just a regular binary result. And you can use that in your program however you wish. So every quantum program follows these steps. There's something called quantum error correction. And this is because qubits are very fragile. Because of the finickiness of quantum mechanics, any little disturbance spoils the quantum nature of them. And so we have to think about things like quantum error correction, in which you spread the information from one qubit among several qubits. And so we do theoretically understand how to do this. Right now, we're not quite at the point where we can do this in practice. About 2 months ago, Google and Honeywell published separate articles in which they were able to do this for one qubit in real time. So this was a major step forward, but we're not quite at the point where we can do this for all programs at a realistic level. So this will be a major advance. When we can finally do this at a practical level, we will really be able to see some sophisticated programs. Right now, since we're not able to do this quantum error correction, we have to kind of make do with the computers that we have. We have to keep the programs short and not include that many operations, because we know that at some point there will probably be an error which will spoil the program. And there's actually a formal term for this. It's called NISQ, or noisy intermediate scale quantum. And it means that the computers we have today are about 100-ish qubits. They have relatively high error rates. We can't take advantage of error correction, as I mentioned. And there's a lot of constraints about how the qubits are coupled to each other. And so to account for this, we have been putting a lot of focus on hybrid algorithms. And so that means that our quantum programs work in conjunction with a classical program. And a lot of the heavy lifting is done by the classical programs, because right now classical computers are more powerful. And so a lot of programs right now, even though we call them quantum algorithms, they're actually more hybrid type algorithms. So what could you do with a quantum computer? Why have we gone to all this effort to build these quantum computers? As I said, there's a lot of programs, a lot of things that we could never do with a normal computer that we think we could solve with a quantum computer. And some of these examples include chemistry, things like drug development and material science, so like designing personalized medicine or designing better batteries. For industry, doing things like supply chain management and logistics and optimization. There's a lot of machine learning problems people use all over. So especially financial institutions, they have trading algorithms. And so we think that we could come up with more efficient and accurate trading algorithms. And then finally in cybersecurity, as I'll talk more about in a few minutes. For machine learning, all quantum machine learning algorithms follow this same basic schematic. So again, each horizontal line there represents a qubit. Reading it from left to right, we prepare the quantum data set. And sometimes this is a bit of a bottleneck because we have to turn the classical data into quantum data before we can evaluate it. Then we evaluate the quantum model and then measure these different qubits. And so again, that measurement process turns all the quantum data back to the classical data. We then evaluate our classical model and give feedback into the quantum operations. And so there's this constant feedback so this is the learning part of the machine learning. And so eventually you should have some sort of minimum or maximum for the function that you're trying to optimize. And so this is the basic schematic of how machine learning works. There's a list now of different quantum algorithms. And so this is a list of some of the popular ones. And in the right-hand column, you'll see that there's speed up, which is either square root of n or log of n. And that's because most quantum algorithms offer either a quadratic or an exponential increase in speed compared to their classical counterpart. And so what we would really like to do is get the exponential speed up. And fortunately, there are some real world type algorithms which can do this. As I said, a lot of financial groups are especially interested in optimization type problems. And fortunately, this is one of the exponential type algorithms that we've dealt with. There's actually a real world type problem, which is being studied right now by Microsoft and Case Western Reserve, and that is radiotherapy. And so when groups treat cancer, they can use radiotherapy, but they don't want to use too much because it could harm the patient. And so there's a lot of optimization type issues, where to apply the radiotherapy and how much to use. And so it's a very ideal problem for this type of machine learning and optimization. And so, yes, Microsoft and Case Western Reserve are already using quantum machine learning for this type of problem. Another example of quantum machine learning being used is in the so-called Knapsack Problem. And this shows up all over the place, from job scheduling to storage optimization. And it's when you have some sort of finite capacity, like a knapsack, which can only carry so much, and you have several objects which you can place into the knapsack. Each of the objects has a weight and a value. So you're trying to maximize the value subject to the constraint that you can only put so much weight into this knapsack. And again, this shows up all over the place in different problems. And our scientific team developed a quantum version of this. And I want to show you here, these are actual outputs from the quantum computer. So regarding the graph on the left here, so you'll notice the horizontal axis represents all the different combinations of which item to put into the knapsack. So if it's a 0, the item is not there. And if it's a 1, it is there. This was a pretty small problem containing only 5 objects. And you'll see that one solution really peaks. So one stands out. It was the result about 72% of the time. And that is the correct solution. So that's good. We could check this with a classical computer. And this is very typical of quantum machine learning. Although it's faster, the trade-off is that you are not guaranteed to get the correct solution. So that's the trade-off when you use a quantum computer. The right-hand graph shows a larger version of the problem. So it had 10 items, and we did this on IBM's quantum simulator. Again, you usually get the correct solution, but not always. And so that's why it's important to run the simulation many times to see what the histogram is. And so usually you can figure out what the correct solution is. The final example of a machine learning type problem that we're working on is natural language processing. And I think that many of you are familiar with this. Devices like Alexa and Siri and chatbots and such use the different natural language processing algorithms to understand what we as humans are saying. So they turn different words into mathematical formula, which they can interpret. It was discovered by our research team that natural language processing has a very natural structure in quantum computing. And so they've been able to translate everything. And actually, just in these few days, we actually had a major announcement talking about a whole natural language processing platform that people will be able to use for this type of thing. So I next want to talk about quantum compilers. I think many of you are probably familiar with compilers from just normal computers. So a compiler is basically just a translator that turns what you program, like Python or C, into instructions for the machine. Because the machine, of course, can only understand instructions for its switches. A good compiler not only does the translation, it does it as efficiently as possible. And it of course, wants to make the program as small as possible, and it wants to make the program run as quickly as possible. It is exactly the same with a quantum compiler, and we have developed our own quantum compiler, which we call Ticket. So Ticket is language agnostic in the sense that you can use any of the popular quantum programming languages like IBM's Qiskit or Google's Cirq or Microsoft's Q#, and you can write your program and then execute it on any of the popular quantum hardware platforms, that by Honeywell or Google or IBM or any of the others that I've mentioned here. So Ticket not only does the translation and execution for you, it does so in the most efficient way possible. It has a lot of subroutines in it to first make your circuit as small as possible, and then find the most efficient way to execute it on the hardware that you've chosen. So it has a lot of different algorithms, and it performs these simplifications. So an example of this, so on the left-hand side here, so this is a typical 5-qubit quantum circuit. So you see, just like before, you have the initialization on the left-hand side, and you have some operations, and then you have measurement. Some of these qubits have 5-qubit coupling, meaning that one qubit will talk to 4 others. The quantum diagram on the right, so this is the IBM Melbourne machine, you'll see that at most it has 4-qubit couplings. So at most, one qubit is talking to 3 others. So naively, we might look at this and say that there's no way to run the program on the left-hand side on the computer on the right-hand side. That's actually not true. You can do it, but you have to do something called swapping. You have to move the information for one qubit around and do this cleverly enough so that you can run the program. So this is the type of thing that Ticket can do. We are always updating it. We have about a monthly update cadence. And so we are constantly updating with the latest hardware and algorithms. Several months ago, we removed all licensing restrictions. So it's completely free to use. You can use it however you wish. If you come up with $1 million app using this, that's fantastic. You don't need to let us know or pay us royalties or anything like that. The URL to download this from GitHub is there at the bottom of the screen. And so I would encourage you to use that. The big news that will be announced in about a week or two is that we are making it completely open source. So anyone can actually go into the source code itself. They can build their own extensions for applying it to whatever hardware they want, and they can add their own efficiency subroutines. So again, that will be announced in the next few days. So the final thing that I'd like to talk about is encryption. And I think many of you are probably familiar with the basics of encryption. When we send sensitive information on the internet, we're usually not sending the information itself. We're sending an encrypted version of that. So what that means is that we apply a complicated mathematical formula to the data, and that's what we send. And the person receiving that has a key where they can undo the encryption. And we do hear about hacking and so forth, but usually the hacking is because of human error. It's because someone left their password on a sticky pad on their desk or something like that. It's usually not because the formula was directly undone. And that's because we use formulas which are purposely so complicated that it would take computers a long, long time to do it. Unfortunately, some of these formulas that we chose decades ago are easily undone by quantum computers. And we didn't know that at the time, of course, because there were no quantum computers. And so this has a lot of security professionals very concerned. It's not something that quantum computers could do right now, but in a few years, it's possible that quantum computers could directly undo these formulas, meaning that anyone could read your email, even if it was so-called encrypted. So that's the bad news. And on this chart here, I show that on the upper part, about 99% of online encryption formulas are vulnerable to quantum computers. The good news is that people have already started developing protections against that. So mathematicians and computer scientists and physicists have already been developing new formulas which we don't think quantum computers could hack. We're not sure yet. This is under investigation right now. The American government agency called NIST is having a contest, and last summer they announced 7 finalists. In the next few years, they will probably announce 1 or 2 winners. So people are investigating them right now to see how sturdy they are against hacking. And so very soon we will probably have 1 or 2 winners. Now, I would not wait until you start reading headlines about hacking to make this upgrade. Because these 7 finalists already exist right now, I would strongly encourage you to begin upgrading right now if you're in a position to do this. And there's 2 reasons for this. The first reason is that it takes time to upgrade. So if you've ever tried to upgrade software for a big corporation or a government agency or something, you know that it can take a long time. The second reason is that there are rumors that hostile governments and bad players are archiving things right now, so that in a few years, when quantum computers are sufficiently powerful, they can decrypt things. So for those reasons, I would strongly encourage you to make that upgrade right now. So I've kind of explained how quantum computing could be used for hacking, but there's a lesser known application in which quantum computers could be used to protect against hacking. And this method is called quantum key distribution. And it's when you transmit quantum data itself. So you don't convert quantum data to classical, you actually send the quantum data itself. And this is usually done using fiber optics or satellites, where they transmit photons, which are kept in a quantum state. It's completely secure because any sort of eavesdropping would require you to measure this quantum data, and that disturbs it. This can be detected. And to better understand this, I'd like to show this video here. So this is a source of entangled qubits. And recall that entanglement means that whatever one qubit is, the other is. So they're in the same state. It's random, but they're in the same state together. And these 2 qubits are then measured independently by 2 different measurement devices. We'll call them Alice and Bob. So Alice measures the first qubit in a random direction, and Bob measures his qubit in a random direction. And then they compare notes. So they don't communicate while they're doing this, but then they compare notes. And if they measured in the same direction, they should always get the same result 100% of the time. And that's because of the entanglement. So now Alice and Bob have a secure key, which is known only to them. Now let's redo this using some sort of eavesdropper. We'll call her Eve. So Eve grabs one of the qubits and measures it and then replaces it in that same configuration. So according to classical physics, this is the perfect crime because we would never know the difference, because Eve has replaced it in the same configuration. But this is not a classical system, it's a quantum system. And so Eve has broken the entanglement by doing this measurement. And so now when Alice and Bob do their measurements, even if they measure in the same direction, they will not always get the same result. And so now when they compare results, they'll notice a large fraction of the time they get different results. And so this is mathematical proof that there was some sort of eavesdropping or tampering going on. You don't need to just trust that the communication is secure. There's actual mathematical evidence. And so this type of quantum key distribution, or QKD network, is something that's being developed right now. There are several governments and companies that are starting to deploy this, again, either with fiber optics on the ground or in space using satellites. So to conclude, and to give you kind of a forecast of what I think the future will be, right now we do have quantum computers and we have developed post-quantum encryption. I think it'll be 3 years or so before we start to see commercial applications of quantum computing. It could be slightly longer than that, but it's not going to be much longer than that. And we could start to see hacking from quantum computers. I think within 8 years, we will absolutely see commercial applications. In fact, I think quantum computers will be fully integrated into existing technology, and you'll probably be using it without even realizing it. And in 8 years, hacking would be likely from quantum computers. So again, I urge you to upgrade if possible. So that was it for my prepared remarks. My email here is given at the bottom if you'd like to get in touch, but I'm happy to stick around and answer any questions that you might have. Thank you.
Thank you, Mark, for your lovely presentation. I think that maybe we have some questions. Es cierto, de nada. ¿Preguntas? Ah, okay.
Nadia?
Well, there is a question from Javier Gomez. He asks if, are you developing, documenting the security risk model framework as well as you do with potential benefits of quantum computing? I read it literally. Do you want to, I will, I could read it again.
Could you translate, please? To make sure I understand.
I think that he's asking about if there is, in the same sense that there is a model about the quantum volume that implies a lot of characteristics of quantum computing, if there is also a model for the business of quantum computing, maybe taking into account investment, budget, reimbursement, etc.
That's a very good question, yes. So we have a model of the science behind quantum computing. The business model is also just emerging because it's very new. It didn't exist commercially a few years ago. So I can speak about our company, first of all. So Cambridge Quantum has developed quantum software for 7 years. And so the compiler we're now giving away for free, but we charge companies to develop quantum applications for them. We usually keep the intellectual property in order to build the applications, but we license the results to our corporate partners so that they can use it in whatever application they want. We're a little bit different from other companies in that we are not a consulting company. So we don't just do a report and then hand it off and say goodbye. So we are really interested in building applications. As I mentioned, we're in the process of merging with Honeywell, who has built quantum hardware, and so they charge for access to that. So companies or groups pay them to use their quantum computer. I'm sure that the business model will have to be adjusted a lot as things emerge. We're now seeing a new quantum startup almost every week. We're seeing literally billions of dollars in investment, and so fortunately, it's now becoming commercially lucrative. But yeah, the business case is not completely determined.
Okay, thank you. There is another question. Should we have a global plan to avoid quantum security attacks? Sooner or later, we will have it, right? The question is from Fabio Grigoriev, I think.
Yes, that's a very good idea. Governments are starting to become increasingly concerned about this, and there is sort of we call it a bit like the Cold War with East versus West, and it's not physical warfare, but it's computer warfare with countries hacking and threatening to hack and such. And so yes, it would be nice to have some sort of agreements and collaboration and truces, but that hasn't really yet happened. We're still sort of in this Cold War standoff, and it's also unclear which countries have actually developed hardware and which are kind of grandstanding and doing things just for promotional scare tactics.
Okay, the next question is for something that is thinking about studying this. I don't know if I can make this question to physicists, but the question is, what degree do you recommend to work in this field? And how do you expect that the quantum software will grow in the next few years?
Yes, so there are tremendous job opportunities in quantum computing. We can't hire fast enough. So if you go to our website, you'll see that we have many openings. We're struggling to hire good people because quantum information science, that's the academic term for this, it didn't exist as a formal degree a few years ago. It's only now that a lot of universities are starting to offer this. So like myself, my background is in physics, specifically string theory and cosmology. So even though I have a PhD in physics, I'm actually on the business side of the company. The people who develop our programs on the scientific team, they usually do have advanced degrees in quantum computing or something very similar, like computational chemistry or something. So I would recommend, if you can, actually get a degree in quantum computing or quantum information science. If you can't, something closely related like physics or mathematics or computer science is very good. Even if you don't intend to actually be a scientist, I would still recommend that you get a degree in this, even if you want to be on the business side, because this is one field where you really do have to know what you're talking about, even to discuss the business side of things. So we really do need smart young people. So I really encourage you to get into.
Okay, I think I get maybe a rather technical question, but the compilers, the quantum compilers that you're providing, I think that there are a lot of limits in space for the programs that can be run because obviously a huge matrix cannot be stored in an actual quantum computer. So how those limits are put into the compiler?
Yes, that's exactly right. In fact, I would even go further. When we use normal computers, we just take for granted that we have RAM, right? We have memory that we can access when we need to. Quantum computers don't yet have quantum RAM or QRAM. Many groups are trying to do this, and we may have it in a few years, but we don't yet have quantum RAM. So what we have to do is, when I showed you that quantum program, we have to initialize the qubits, operate on them, and then measure them all very quickly. There's not time to store it and then come back to it later as we need to. So we have to make the program very small and execute things as quickly as possible. And so that has placed a very severe limit on what we can do. That's why we call it NISQ era. So we have to make the programs as short as possible because anything larger will not work. So yes, that's exactly right. Right now, we don't have that many qubits and we can't do that many operations on them. In a few years, I think that will be different. Once we do quantum error correction, then we will be able to have more sophisticated programs.
I think that there is another question that nobody wants to ask, but how is the budget for purchasing the IBM machine, for example? I mean, so, IBM sells the chip one with the 49 qubits. The electronics must be purchased separately. So, but do you have an idea of the budget?
I do have an idea of the budget. So first let me say IBM has done a fantastic job of making publicly available for free a lot of resources. So it's called Qiskit, Qiskit. That's the name of their development platform. And they have done a great job of making a lot of examples and notebooks available for free. And you can access their low-end machines having 5 qubits or maybe a few more for free. There may be a bit of a wait because other people are trying to use it, but you can use an actual quantum computer in their laboratory in New York for free. The higher end machines, the one you mentioned with 49 qubits, it is not free. My understanding is that you would need a 3-year contract, which costs about $1 million per year. So it's about a $3 million budget to use their high-end machine, which I realize is probably out of the budget of most of you sitting there. we have a close partnership with IBM, and so we are able to provide access to their high-end machines at a much lower budget. We can give it in increments of 6 months, and you would share it with a few other partners, including us. And so that's much more palatable to many groups' budgets. So yes, the higher-end quantum machines are a bit expensive for.
I don't know. We have a time for a last question, or? Okay, I think that maybe another technical question. When was proved that the encryption method based in elliptic curves was quantum breakable? 2 years ago, or?
For elliptic curves, I don't know. For RSA, which is based on the difficulty of factoring large numbers, I think it was 91. I could be wrong, but for some reason I think that. So to explain a little more about that, you might have noticed that if I gave you 2 numbers to multiply, it's easy to do that, right? With a pencil and paper, you know how to multiply numbers and get the result. But if I give you a large number, it's very difficult for you to figure out the 2 prime numbers that you would need to multiply to get that number. And that's because no one has ever found a fast way to do that. You basically have to guess and check if a number is a factor. And so that's why they use this for RSA encryption, because a computer would have to guess and check every prime number up until the big one. And so it turns out that quantum computers are very good at this. And this was realized by someone named Peter Shor, who's kind of one of the grandfathers in quantum computing. He realized many years ago that quantum computers can do the factoring exponentially faster. So even if you give it a large number, quantum computers could do it very efficiently if the quantum computer were sufficiently powerful. So we can't do it today, but in a few years it might be possible.
Okay, do you send it or? Okay. I think so. Yeah. Do you want it? Yeah. Do it. Just do it. There is another question, but the person that got the question wants to ask you personally. Okay.
Okay.
Hi. I want to ask you that you mentioned language processing, but you gave an example in English. How do you handle this problem with other languages?
That's a very good question. Yes, that's true. The only examples I've seen were in English, and that might just be a prejudice because a lot of science is done in English. But I'm sure every language has its own structure, right? There's different rules for grammar and understanding the meaning of a sentence. And so I'm sure that we will also need, for example, Spanish natural language processing, because of course you would speak to Alexa or Siri in Spanish as well. And so yes, these areas are also needed.
Okay, thank you. I think that there are not. No, we're in time. We thank again to Mark. Thank you very much for the organizer, for ourselves. Thank you.
Thank you again, and I hope to join you in person next year.